Hello everyone, I'm Farhad from ECEC section. Today I'm going to talk about the ordinary differential equation in theory and practice. Before jumping into the topic, let's have a look about what is a differential equation. A differential equation is an equation involving an unknown function and its derivatives. By a solution of differential equation, we mean a function that is differentiable and satisfies the equation on some interval. For example, x dash minus x is equal to 0 is a differential equation involving an unknown function x and its first derivative with respect to an independent variable that we may call t, s, etc. We notice that e to the power t dash minus e to the power t is equal to e to the power t minus e to the power t is equal to 0 for all t in the interval I, which is minus infinity to plus infinity. Therefore, x of t is equal to e to the power t is a solution of differential equation on the interval I. Here is the formula which we use to derive a differential equation. Ordinary differential equations. An ordinary differential equation contains the derivative of an unknown function. The ordinary differential equation is an equation having variables and a derivative of the dependent variable with reference to the independent variable. The two types of ordinary differential equations are the homogeneous differential equation and non-homogeneous differential equation. Ordinary differential equations applications in real life include its use to calculate the movement or flow of electricity, to study the to and fro motion of a pendulum, to check the growth of diseases in graphical representation, mathematical models involving population growth, and in radioactive decay studies. Here is the general formula of ordinary differential equations. What is an ordinary differential equation? The derivative of the dependent variable with reference to only one independent variable is called the ordinary differential equation. A differential equation is an equation having variables and a derivative of the dependent variable with reference to the independent variable. The notation used for derivatives in these ordinary differential equations are the first derivative dy by dx, second derivative d square y by dx square, third derivative d cube y by dx cube, and nth derivative d to the power n y by dx to the power n. Here are some examples of ordinary differential equations. Order and degree of ordinary differential equations. The two important aspects of ordinary differential equations is the order of differential equation and the degree of differential equations. We can use a graph to determine the order and degree of differential equations. Order of ordinary differential equations. The order of a differential equation is the order of highest derivative of the dependent variable with respect to the independent variable. Here are some examples of differential equations. In these differential equations, the highest order of the derivative are of first, fourth, and third order. First order differential equation. It is the first order differential equation that has a degree equal to 1. All the linear equations in the form of derivatives are in the first order. It has only the first derivative, such as dy by dx, where x and y are the two variables and is represented as dy by dx is equal to f of x comma y is equal to y dash. It is an equation of form f of t comma y dash is equal to 0. A solution of a first order differential equation is a function f of t that makes f of t comma f of t comma f dash of t is equal to 0 for every value of it. Second order differential equation. The equation which involves second order derivatives is the second order differential equation. It is represented as d by dx of dy by dx is equal to d square y by dx square is equal to f double dash of x is equal to y double dash. Here is the general representation of second order differential equation. And here is the example of second order derivative from which we can find the second order. Degree of ordinary differential equation. If a differential equation is expressible in a polynomial form, then the integral power of the highest order derivative that appears is called the degree of differential equation. The degree of differential equation is the power of highest order derivative present in the equation. To find the degree of differential equation, we need to have a positive integer as the index of each derivative. For example, in this question, we have to find the order and degree of this differential equation. The order of this equation is 1 and the degree is also equal to 1. Types of ordinary differential equations. The ordinary differential equations are broadly classified as homogeneous differential equations and non-homogeneous differential equations. Homogeneous equations, a differential equation in which the degree of all the terms is the same, is known as homogeneous differential equation. In general, they can be represented as p of x comma y of dx plus q of x comma y of dy is equal to 0, where p of x comma y and q of x comma y are homogeneous functions of the same degree. Non-homogeneous equations. A differential equation in which the degree of all the terms is not the same is known as non-homogeneous differential equation. For example, xy of dy by dx plus y square plus 2x is equal to 0 is not a homogeneous differential equation. Linear ordinary differential equations. A linear differential equation is a differential equation that is defined by a linear polynomial in the unknown function and its derivatives, that is an equation of the form a naught of x into y plus a1 of x into y dash plus a2 of x into y double dash plus so on plus an of x y to the power n is equal to b of x, where a naught of x so on a to the an x and b of x are arbitrary differentiable functions that do not need to be linear, and y dash so on y to the power n are the successive derivatives of an unknown function y of the variable x. Solving linear differential equations. First, we need to determine the function of independent variable, let us say m of x, which is known as the integrating factor. Multiply both sides of equation 1 with the integrating factor m of x. Now, we choose m of x in such a way that LHS of equation 2 becomes the derivative of y into m of x. Then integrate both sides with respect to x, we get this equation. Now, using this value of the integrating factor, we can find out the solution of first order linear differential equation. Multiply both sides of the equation 1 by integrating factor, we get this equation. This could be rewritten as, now integrating the sides with respect to x, we get this equation. First order linear differential equations. A first order differential equation is the linear when it can be made to look like this. dy by dx plus p of x y is equal to q of x, where p of x and q of x are functions of x. We also use the derivative of u is equal to y is equal to uv, dy by dx is equal to u dv by dx plus v du by dx. Here is the first order differential equations. Steps to solve the first order linear differential equations. Substitute y is equal to uv and dy by dx is equal to u dv by dx plus v du by dx into dy by dx plus p of x into y is equal to q of x. Factor the parts involving v. Put the v term equal to 0. Solve using separation of variables to find u. Substitute u back into the equation we got at step 2. Solve that to find v. Finally, substitute u and v into y is equal to uv to get our solution. Example. Step 1. Let's substitute u is equal to y is equal to uv and dy by dx. Factor the parts involving v. Putting the v term equal to 0. Solving using separation of variables to find u. Substitute u back into the equation 2. Solve this to find v. Make C is equal to ln of C. Substitute into y is equal to uv to find the solution of the original equation. This is the solution of the original equation. Second order linear differential equations. To solve a linear second order differential equation of form d square y by dx square plus p dy by dx plus qy is equal to 0, where p and q are constants, we must find the roots of characteristic equation r square plus pr plus q is equal to 0. There are three cases depending on the discriminant p square minus 4q. When it is positive, we get two real roots and the solution is y equal to a e to the power r1 to the power x plus b is equal to e to the power r2 to the power x. 0, we get one real root and the solution is y is equal to a e to the power rx plus bx e to the power rx. When negative, we get two complex roots. R1 is equal to v plus wi and R2 is equal to v minus wi. And the solution is y is equal to e to the power vx into c cos wx plus id sine wx. Positive roots. Let us take an example to find the two real roots. The characteristic equation is factors the general solution of our differential equation. When roots are 0, the characteristic equation is this. So we have only one solution, which is y equal to e to the power 5x. But when e to the power 5x is a solution, then x e to the power 5x is also a solution. Negative roots. We'll get, in this case, we'll get complex roots. For example, by using quadratic equation formula, we get the solution y is equal to e to the power 3x into c cos 4x plus id sine into 4x. Non-linear differential equations. A non-linear differential equation is a differential equation that is not a linear equation in the unknown function, and its derivatives, the linearity or non-linearity in the arguments of the function are not considered here. Examples: y double dash plus y is equal to 0. And here are some more examples of non-linear differential equations. Thank you so much.